In this video, I'm going to be demonstrating the use of IES Visual Analysis software for the structural analysis of a two-story rigid frame structure. The loads are as shown in the diagram here. Those loads will be computed in a separate video, so please take a look at that for that information. This will focus only on the analysis of the frame. Design parameters include a allowable beam deflection of L over 300, so for a 30-foot wide frame, that gives me 1.8 inches, and an allowable frame drift, that is the displacement at the top of the frame, of H over 200, which comes out to 1.56, about 1.6 inches. So to begin with, we will start by making a new structure. We want to make this a plane frame structure so we don't have to worry about out-of-plane actions. It minimizes our number of restraints on the ground. So we'll start by drawing the columns. These are 14 feet tall, and you see as I drag this, it is reading out on the bottom here the length. So I'll drag that up to 14 feet, and it's snapping to the grid there. It remembers the last selection. The XY axes here, they're kind of large. So I'm going to actually go and turn those off so they don't obstruct my view. And while I've got this, I think I'll make a support for that. And I'm going to shift, click, drag everything there, and right click and do generate copies. And I want to create one copy in the X direction. It's going to be spaced at 30 feet and 0 feet Y. And there is our copy, and that automatically gives us the same restraints on the base. Next, we'll draw our 12-foot columns on the top, right there, and one right here, and lastly the beams. So that is our basic structure. Good idea to save the project at this point. I'm going to save this as a demonstration project here. You can give it any name you want. Now, speaking of names, what I'd like to do is give these sections names that are intelligible. They will have a default name here, call 001. I'm going to label that call L for left, 1 for first floor. And then I'll just speed up the video as I go through naming these other members. All right, now I have all the names done. The reason I do that is because it makes the results much easier to read. And in fact, we can also turn on names. If we go to the model filter, name is by default, it's turned off. If I click on that, now we have the names visible. We can also show the lengths as well, but there's, beyond a certain amount of information, it gets to be too much to be seen here, so maybe I'll leave that off. Next, we create the loads. So go to the loading tab, and we're going to start with Load Case Manager. And by default, we have ASCE 7-16 LRFD. That's the American Society of Civil Engineers. 7 is the code, 16 is the year, LRFD, load and resistance factor design. That is a specific specification, as are all of these others here. So we're going to just click that off. We're not going to use that. Now if we go to our service cases, by default we have a dead load, and it's included in the analysis. For our purposes here, we're just going to turn that off and keep this really simple. We're going to create a service case called gravity. And this includes our dead loads and live loads. Notice the load source here. This does not matter for our purposes. This is elements of the program you're not going to be using. So it'll just be gravity. And we create another one called wind. And the same as previously, we just leave that to live. There is a option here to change that to wind, but we're not using those features here. Now it looks like nothing's in here. It's because there are empty cases are not shown, which means there's no loads on them. So these are all the built-in types of loads you can have. Here's the ones we created, gravity and wind. They're both without any loads at this point, so they don't show up. I want to actually uncheck include in the analysis to simplify things, because that's going to be combined in a load combination. You can't have wind all by itself. Wind has to occur at least with dead load and certainly with a little bit of live load. So that's where load combinations come in. We're going to create a factored combination. We'll keep this one simple too. We'll call this gravity plus wind. And down at the bottom you'll find the gravity and wind loads. We're going to put a factor of 1 on these. So it's 100% of gravity and 100% of wind. All of these different specifications have many different combinations with different factors, less than 100% or even more than 100%. To cover the greatest probable likelihood of any of these happening at the same time. You're not going to get 100% of wind and seismic and earthquake and full live load all at the same time. So that's what that is. But we're keeping our things simple here. So we create the load cases. Now we can create the individual loads. So over here you see zeros. That means there are 0 forces in these. So no loads yet. I want to find gravity right here. And now I can put my loads on here. We start with the member load on the roof. This is going to be a force in the Y direction. And I had previously done this so it remembered my 0.25 kips per foot. It's going to be uniform on the entire length of the member, so that's good. And the second beam also has a uniform load. This is going to be 3 times as much, so 0.75 kips per foot. Next we have nodal loads at the top and second floor beam. I'm going to click on the node and then there we go. Turns purple when it's clicked. Control click on the next node so I have both of them selected and apply a nodal load. This will be a force in the Y direction. At the roof level this will be negative 7.5 kips. And that shows up here. Graphics sometimes go off the screen with visual analysis. Again, click and then control click for the second one. Apply another nodal load and this will be negative 22.5 kips. And at this point I like to save my model because you never know what's going to happen. So there's my gravity loads. Now for the wind load, so I have to go down to my empty wind load case. And I have a nodal load at the top. It's a force X of 3.6 kips. And at the second floor, another nodal load of 7.8 kips. So that's our model. It is complete at this point, and placeholder members in here. So we can take a quick look at the performance. Just jump to the report view. And first off, there's nothing here because we don't have a report selected. So I'm going to use my previously created basic maximum stresses. And we can see right off that many of these forces are quite a bit higher than allowable, and the deformation is way too high. We have a almost 5-inch column drift here. We are allowed 1.6 inches. So things have to change. Let's just start out with the stresses. So for this, we can see that the worst case is the combined stress here, 45.63, due to the case gravity plus wind. So that's taking the bending stress is 45.49 and then adding the 0.13 to that to give you the max, because this is combined axial load plus bending stress. We don't have to worry about buckling for the beam because it's restrained by the rest of the structure. It's tied on to the deck. So we really just look at this combined stress here. Now, if I go back to my results view and go to member forces, the most stress beam is going to be the second floor here, and I can see that I have a under wind load, gravity plus wind load, 122.76 kip feet. So let's pull up a calculator here. And I'm going to take that 122.76 and multiply that by 12. That gives us kip inches divided by the 22 KSI is our allowable. We need a section modulus of about 67 for that. So if I come over to my allowable stress selection table, I can see a W 18 by 40 has a section modulus of 68.4. So let's try changing this to a W 18 by 40. This may not be the final selection as other parts of the structure interact, but it will get us much closer. And then the roof beam, have a look at that. So we can see that 18 by 40 is now down to 22 KSI, so that's still a little bit overstressed. The roof is actually understressed at the roof beam 12.52, so it's got a lot of extra capacity, and its deformation, it's not showing up here. The reason is this is selected for extreme rows only, so let's change that to show all. Okay, that's a pretty small amount of deflection, only 0.29 inches. So we have plenty of stiffness. This is really a stress issue. So we'll go back to our model here. That 10 by 30. Now by trial, I arrived at a W 12 by 19 for this. Can go through the same process that I did for the beam on the second floor, and this is a little bit overstressed, so let's bump that up by one section size to a W 18 by 46. Now let's look at our results, and we see 19 KSI stress for the second floor, 18 for the roof. That's great. Deformations are good, except the drift. Now we have an issue with drift on the columns, and also the column stresses are way too high. That's well over 22, so we definitely need bigger columns. So we're going to increase the column size. And I can start with the moment as a way to begin. So just like I did with the beams, let's go to the result view here, and I'm going to turn on the gravity plus wind. And while we're on this, let's also show the undisplaced just for reference. It shows our loads as well. So I'm interested in this column on the bottom here. That is going to be the most heavily loaded column, and it has a bending stress of 93.55 kip feet on it. So let's take 93.55, multiply that by 12 inches per foot to get kip inches, divide that by 22 KSI. It says we need a section modulus of about 51. So again, I come over here, what has 51? Keeping in mind this is a column section, I don't want it too big. I see a 16 by 31 is close, 16 by 36, or you could go to 18 by 35. Let's try the 16 by 36. Now I'm going to change all of the columns this way, so I'll go back to my model view, and if I come down here into this find tool, I can select all those members in the table. So you have two ways of selecting things. So let's change this to the W16, and again we're looking at a W16 by 36. And let's see how our stresses and deformations are. So we're getting closer. 25 KSI here. Still a little bit too much drift. Again, what we're allowed on the drift is 1.6, so we're close, but just a little bit over. So now I did a few other iterations on this, and I arrived at a W16 by 45 for these members here. And now everything is looking good stress-wise. The deformations are low. The last thing to check is the combined stress on the column. We have to look at beyond just this 20 KSI here. We actually, and that's the controlling factor, because it's the axial force plus bending. Here's the bending stress, and then the axial stress is 3.89. What we need to find out is the allowable stress for a W16 by 45 when used as a column section in axial load. So for that 16 by 45, let's go back to our shapes table now. Here's W16 by 45. Come over here. I see my radius of gyration in the y-axis is 1.57. So I want my get my length of 14 feet. It's 14-foot tall column times 12 to get it into inches. Now there's restraint on this column, so the K value is not going to be 1. It's going to be closer to 0.7. It's actually not going to be quite that good, but for our purposes we'll just call it fixed, and so it'll be 0.7. So our effective length is about 120 inches, 117.6. Now divide that by 1.57. That gives us our slenderness ratio of 75. So we go to the column table now, and on our first page, this is the older edition of the American Institute of Steel Construction Steel Manual. Go to 75, and I see I have 15.9 KSI is allowable. And in my structure, I'm using 3.89. So we'll take 3.89, and our allowable again, 15.9. Using about 24% of the allowable capacity just for the axial load. Then the bending stress that is based on 22 KSI allowable. So I'll take that 16.27. Divide that by 22, so another 74% there, and then we add those together, 0.98. So I'm right on the money. So that's going to be our final selection here. And there's a loading and the final results and the deformed shape under loads. Now that we've analyzed the structure, we can look at it under varying conditions. For example, perhaps fix the base, so I have a moment connection at the base. What happens to the structure? Well, we can see in the result view, the graphics, a different kind of behavior at the base. There's bending here now when this was not having that happen. And we can see that the displacements are quite a bit reduced. This maximum is 0.51 inches. Previously it was about 1.4, so it's gone down by almost an inch just by fixing those bases. Also, we find that our stresses go down, so that means that we can use smaller members. It's because we're getting helped by the resistance at the base here, and that's traveling both up the column and a little bit into the beam. So we'd see a reduction in the cost of materials. But there'd be a downside that the base would have to have a foundation that could carry moment. So there's always a trade-off. So that would be one possible change that we might make. Another one might be what happens if we alter the direction of our members, the orientation rather. I'm going to look at this in 3D view and with the picture view on. So we can see that all of the bending is happening about the major axis. So I'm going to turn those axes back on here. And I guess they're always down at the bottom here. So Z is out from the page. So when we say bending about the Z-axis, it's kind of like an axle. It's rotating about that. And now if I take all of those columns and change what's called the beta angle, it's the angle along the x-axis, which is always along the length of the beam. I'm going to change that to 90 degrees. And so what we see now is the columns are bending about their minor axis. So let's go back to the front view here. And we see it looks a lot more slender. And what happens with the analysis, look at the result here, particularly under the wind load, get more drift on this, and the actual numbers tell us that we have almost 11 inches of movement here. Now the drift is in the z-axis because it's always relative to the member, and in this case, turn on the picture for this, the z-axis for this is going left to right as we're looking at it on the screen. So that's not a good situation there. We're going to need a lot bigger member. And look at the stresses here. That column is up to 113 KSI. So you have to play around a lot to make that a good structure. So generally speaking, we want to avoid the minor axis bending unless there is some other overriding concern. So let's turn those back. Now the other thing that we can do is perhaps change this into a braced frame. So what I'm going to do here, draw members on my structure tab. I'm going to go ahead and turn off that picture view so I can see my nodes. I'm just going to draw two diagonals here. And I'm also going to turn off the axes once again. And set the structure to draw nothing so I don't accidentally draw stuff. Now I've got two braces here. First off, they are remembering that I had W12 by 19 as my last member that was selected up on the roof here. So let's change this to something a little bit smaller. We don't usually use wide flange members like that for most braces unless you have a very large building. So for smaller structures, channels are very nice because you can set them back to back. The bracing here is being shown in only one direction. If this is tension only bracing, we would have to have cross bracing going in the other direction, and you set the channels back to back and it makes for a nice connection. Also double angles like this, back to back channel looks just the same except there are flanges down here. So we'll look at just a single channel and we'll get something small like a C4 by 4.5, and let's give it a nice name. So I will call the bottom one Brace 1, and the top one will be Brace 2. And the last thing we need to do, because this is now a braced frame structure, we don't need those moment connections. So I'm going to shift drag to select all of the members in the second floor level, plus control click on the brace. All of these are going to be set to simple connect. So they have rotation available at all the ends. For these two columns on the bottom floor, those I want to be rigid simple. So it's only going to be pinned at the top. If I have a pin down here, I have an unstable structure. So let's just demonstrate that. I've changed that to simple connect. If I look at the results view, it doesn't work. It fails because it's unstable. You have a pin on top of a pin. So make sure to have those as rigid simple. The order of this is the same order that the member was drawn. So the first node is the rigid, the second is the simple. So rigid down here, simple up here. And so now this is ready to analyze. It does analyze both under gravity and wind. And if I look at my, oops, not the member graph. Actually, that's a good way to verify things. If I look at this brace here, I should have no moment on this. And I see no moment. So that's good. That's what I want to see. That's because it's pin connection, ideally. So let's look at the report view. And we see that the lateral drift is at the top. That's only 0.2 inches, so it's really, really stiff compared to the rigid frame condition. Stresses are also quite a bit lower, so I can go through a process here of reducing these members. The other thing working in our favor is the column only has to carry axial load. There is no bending in this column. So if I look at column on the left there, again, you see no bending. So that means it's just a pure column behavior. So I've already got this one solved. So this is the same structure that I had previously, only with the braced frame, and these are the members that I get. So now I have here side by side my optimized braced frame structure and the previously designed rigid frame structure, and we can see the difference in the member sizes. The moment frame particularly has very large columns, W16 by 45s compared to the W16 6x15s on the braced frame. So they are basically 3 times as heavy and more than, almost 3 times as deep as the braced frame. So it's an interesting thing. We can take a look at this in terms of the total amount of steel it's used. So we go to our report view. I'm going to do a report here that I've set up called Bill of Materials Only. That's simply created by selecting only this top one here and creating a new report. So if I started out with an empty report, I could just double click on Bill of Materials, and that's showing me all of the materials here. And same thing for the moment frame. Let's look at the Bill of Materials. Now what I'm going to do here, I'm particularly interested in the weight, total weight. So Visual Analysis allows me to copy all of this to the clipboard in a tab delimited format. Don't use comma delimited, use tab delimited. And now I can go to Excel and paste that information into here. And here we can do a calculation on the total weight, just do a sum of all of that. And I'm going to, this is in kips, let's turn this to pounds. Multiply that by 1,000, so 4,310 pounds. That's the total weight of steel of the rigid frame. So let me just go ahead and label this, label that rigid frame. Next, go back to our frame. I'll do the same thing for the braced frame. Copy the tab delimited and paste that into structure here. So this is going to be the braced frame. just copying formats there. And I'm just going to copy this whole equation down here and make sure my cells are all selected. So not quite half of the weight. We can also look at this in terms of cost. If in-place steel, that includes the extraction of the ore, the transport to the smelting place, the fabrication, cutting the holes, cutting to length, shipping it to the site, the painting, the erection, comes down to about $2 a pound as a rough rule of thumb here. So I'm going to take 2 times the weight, and this is dollars here. Copy that formula down here. And that as a percentage difference, so it's only 58% of the rigid frame. So it's quite a bit of savings. Now the downside, though, is that we're talking about a diagonal brace that may or may not be okay. So there's always benefits and liabilities to different choices that we make. Rigid frame has a lot of flexibility. It doesn't interrupt any spaces, but at the cost of much more expense and much more complicated connections. Brace frame is very simple. It's the least costly, but it is going to require a diagonal member that may not be acceptable. So we often see these in exterior walls, embedded into stairwell shafts, anything that doesn't have an opening requirement. And with that, I think we will end this video, and thank you for watching.